Okay, well, thanks for your patience again, especially with the technology. Hopefully, next year when I'm in Chile, maybe I'll get to visit your campus in Santiago too. We have to just figure out the logistics for that because between the buses and the Santiago traffic and everything, it can be a little challenging. So anyways, this work I'm going to describe, I picked out this seminar because I thought it would match well with showing some of my continuing research, but also match well with some of the things you might be doing with your research or with your students, because it has quite a, it's analytical, but also quite a business flavor. And I had the slides translated to Spanish because just to make it clearer for everybody. And I'm studying Spanish, but my Spanish is muy poco y muy malo, so I'm obviously going to speak in English. It was translated by one of my PhD students who's from Mexico. So if it doesn't look like Chilean Spanish, it's not. It's Mexican Spanish, but I think it's pretty similar. So this work was done with Haluk Yapacioğlu, who was my PhD student. He has since graduated, and he's an assistant professor in Turkey, which is his home country. That's a picture of him, and there's a picture of him with his horse in the U.S. He liked being with horses. I also want to thank the Fulbright Association here in Chile because they're actually sponsoring my stay here. And I'm from the Auburn University, which I'm going to tell you a little bit more about it also. So here's the agenda. It's pretty straightforward what we're going to do. I'm going to have a little background about myself and my university, and then we'll talk about facility layout, and then especially for service industries, including this application, which is in the retail industry. I'm going to describe the model we developed, describe a couple methods for solving that involve Tabu search, with first one objective and then with two objectives. And we'll conclude with some discussion. So pretty straightforward. And please, if you have any questions here, feel free to ask them, or in Santiago, ask through Rodolfo, and he can relay to me. So you didn't see the video there in Santiago, but I can tell you Auburn University, a lot of people don't know where it is. It's actually very close to Atlanta. I use the airport in Atlanta. It's 90 minutes by car from Atlanta, but we're actually in the state of Alabama. Here's Florida, Miami, Atlanta. So that's where it's located. It's quite an old university by the Americas standards, 170 years old, about 27,000 students. And you can see it's a full-featured university. It has engineering, business, education, liberal arts, agriculture, the sciences, the fine arts, pretty much everything. We have a couple of mascots. We have a tiger who's not a real tiger, you can see in the photo. And then we do have actually a real eagle. So that's, we have two mascots. I don't know why we have two, it's unusual, but we do. One wasn't enough. This is another view of the campus. The big building towards the left, upper left, is our library, which is really awesome. It's actually ranked in the top 5 academic libraries in the country, in the US. So this is our football stadium, of course, football Americano. And it looks like this in the fall, so in our autumn, starting beginning of September into early December, usually once a week. We play a football game and people are really excited, and the football stadium seats almost 90,000 people. So it's really kind of an incredible experience. So a little bit more about me. My first degree is in civil engineering, and that's from Rice University in Houston, Texas. I also got a master's in business administration from St. Louis University, which is in St. Louis. It's a Jesuit university. And then a PhD in engineering management and systems engineering from the Missouri University of Science and Technology. I started, after I got my PhD University of Pittsburgh, which is in Pennsylvania, in industrial engineering. And then 17 years ago, I moved to Auburn University. I had a chance to be the department chair and also professor, of course. Before that, I worked at Southwestern Bell in telecommunications. So some of my work, not that I'm describing here, involves some network design work, which kind of draws on that experience in telecommunications. And so I was department chair for 12 years. It was a long time. And since then, I've been on the faculty teaching, and I've really started working a lot in international things. I was really fortunate with Fulbright. I don't think they'll give me any more money. It's my third. So I taught at Bilkent University in Turkey 4 years ago. Last year I was in AFET, which is in Medellin, Colombia, just a short visit to teach for them. And then this year I have a sabbatical, and so I'm at the Catholic University here in Valparaiso, working on a research on some container port logistics. And also I'm teaching a class at the graduate level, which is on fuzzy systems. So I'm just finishing that up. I've been here 3 months, and I'll actually be returning to the US on Friday. So I'm happy to go home, but I'm also very sad because I've been very happy in Chile. But the good news is I will be back next year, so I already have plans to do that, at least for 1 month, hopefully longer. So it's been a really good relationship with me. My area is modeling and optimization of complex systems, and I specialize in computational techniques inspired by natural systems. So things like neural networks or genetic algorithms, I've done a lot of work in both of them. I have several projects in the US, including one with NASA about mission and quality assurance for space payloads, and a couple of simulation-based work for Department of Defense. In the US, a lot of projects are funded for better or worse. I think worse sometimes by defense, but we work on that a lot. And a lot of different collaborations. I've worked with people in, well, I've hosted people from all continents except for Antarctica, of course, and actually Australia. I'm still waiting for someone from Australia. But all the others, I've had students and faculty from Europe, from the Middle East, from Africa, Asia, and of course from Latin America. So it's been a really rewarding for me. And the last 2 years, not this year, but 2 years prior, I had what's called a MEC project in Tennessee, and that's for foreign professors to come work on a research project in Chile. And I worked on the same project I'm continuing, which is on container logistics. So there's me at the Port of Valparaiso with a bunch of other people that we hosted a workshop on logistics a few years ago here in Chile, international workshop. Up top is an older picture. My first big research project after I graduated was to improve the production of that product, which you can see is a toilet. So we were working with the company to make their process better. And it was a really good project for me, but kind of a humble way to start. So we'll get in now to the talk. So I've worked in facility design and especially in what's known as block layout for almost 25 years, since the early 1990s. I didn't do it for my dissertation, but right after I graduated, I started working on these problems. And most of the literature and what I worked on for many years involved manufacturing. So in manufacturing design, the main thing is to try to minimize the cost of material handling. And so you want to put departments or functional areas that have strong interactions close together, because it reduces the time and the effort to move things through the manufacturing environment. There's also some concern with adjacencies. So for example, if you have sequential processes, you could place them together. Or for example, if you have a department that's doing painting, for example, you may want it to be far away from another department or functional area that's more sensitive to either fumes or contamination. So in the work I'm going to describe to you, which is on the retail, we're kind of throw out this idea of things with strong interaction have to be close together. So we're not going to do that because it's not really appropriate. But we are going to use the notion of adjacency. So if you look in the literature, the academic literature in facility design stretches back literally to the 1950s. It's very old in terms of operations research and analytic approaches. But I would say 99.9% of it all pertains to manufacturing. There's very, very little work done analytically in layout and facility design for service industries. So this is something I wanted to start working on because I thought hardly anyone's doing this work. And if you think about service industries and what we're going to discuss here, retail, it's much easier to redesign a facility than it is in manufacturing. In manufacturing, you usually have to move heavy equipment around. You might have certain things like certain electricity or plumbing or ventilation needed. But in the retail and a lot of the other service industries, this is not true. So I was particularly interested in both retail and in healthcare because those are the really two biggest ones. My original thought was try to make a generic service industry approach, but I couldn't figure a way to do that really reasonably. So this work, as you'll see, it focuses on the retail design. And we picked that because it's a huge market segment worldwide and it's ubiquitous. I mean, there's retailers everywhere. And as I said, the barriers to redesigning or moving things around in a retail environment are not so great. I mean, stores can do it pretty easily, and in fact, they do it. But there's almost no analytic work that's been done on this. Plus, I like shopping, and I know shopping, so that was another motivation. But what are some of the differences? So when we started on this work, we were thinking that the movement of material is not that relevant. If you go to a store as the customer, you pick up the materials you want. So I was at the Jumbo last night, along with, I think, everybody else in Villa and Valparaiso. It was so crowded. But I have my card, and I'm picking up what I want to buy, and I take it, and then I take it with me. So the idea of minimizing material handling or products, the movement of products is not really appropriate. But what is appropriate is how the customer interacts with the facility, how the customer moves around the facility. And why is that important? Well, that's important because that is correlated, at least to some degree, with the amount of goods the customer will buy. So if I'm working with the retailer, what is their goal? Their goal is to maximize profits. They want to make as much money as possible. So I'm going to use the term revenues and profits to being the same here. I know it's not the same, but obviously they're correlated in a way that could be calculated. So I'm going to talk about revenues, but what I really mean are profits, because you can have lots of revenues, but if you don't have a lot of profits, it's not good. And we also have to talk about how people get in and out. And one thing that we did retain from the manufacturing literature is the notion of adjacency, because that is still appropriate to retail environments. So what we decided to do was to focus on a particular type of retailer, and what we picked was what in the US is called a department store. Here it would be like a Fabella or a Ripley or something like that. This is an actual layout from a store called Kohl's in the US, Kohls. It's very popular in the US and it's been growing a lot. And one of the reasons that experts say it's been growing a lot is because of their design. So this is the typical design. It's one level, and it's what's called a racetrack design. So it's called a racetrack because this center aisle, which goes in this, it's kind of a rectangle. It's not an oval, but it's like a racetrack. So customers come from the bottom. In this store, there's two entrance and exits at the bottom. And then they're immediately kind of made to go on the racetrack. What they found is customers like the racetrack idea because it makes it easy for them to navigate through the store. And retailers like it because it pushes the customer through as much of the store as possible. Now, why is that important? So I want you to think about the last time you went to a store. So last night I went to Jumbo, and I'm sure probably this weekend, all of you probably went to at least one store. Did you buy something you didn't intend to buy? Almost always, right? So that's called an impulse purchase. An impulse purchase is where the decision to buy the item is made in the store. You don't go in with the pre-idea that I'm going to go buy this. So, and it's not 100% of purchases, of course, but it's a large percentage. And so one thing that retailers really want to do is to increase impulse purchases. And we're going to see that as a main objective here when we develop our model. So I just talked about impulse purchases. And this varies a lot according to the goods. So if you think about, let's say, milk. So milk, at least in the US, I think it's probably true in Chile, is not so much an impulse purchase. You go to the store, you know you need milk. Okay, I'm going to buy milk. Or bread. I need bread. But what's an impulse purchase? Maybe candy. Okay, so if you think about candy, where is candy located? Well, it's back in the shelves, but it's also at the checkout. So that's true in the US, it's true in Chile, candy and gum. And so you're standing there, you're waiting to get out, and you're thinking, oh, well, maybe I can have this candy, or I need some gum. So this is an impulse purchase, which in this case, in candy, it's a large percentage of the sales. And so it varies a lot. And of course, it varies according also to the traffic. So we're going to talk about traffic in the store. And by that, I mean how many customers are actually going in a particular physical area of a store. So the first thing, though, that we're going to talk about is the relationship of space to revenue. So and we're going to talk about departments. When I mention departments in a store, I mean areas that have goods of similar types. So if it's a grocery store, for example, the dairy. So you might have the yogurts, the creams, the milks, and they're usually together. You might have the cereals, the breakfast cereals in one place, the candies in one place. In department stores, usually you have certain women's clothing, like women's sports clothing, women's dress clothing, women's shoes, and then you have the men's, and you have things like household goods, electronics, toys, and so on. So that's what we mean by department. And if you think about that, so let's think about women's sportswear. So if I go to Ripley and I want to buy, I don't know, a t-shirt to work out in, if there's more room in Ripley for displaying and stocking goods, then they should sell more. Why? Because they can have more variety that might appeal to customers and more sizes and colors and so on. But it tends to be of what's called diminishing returns. So if you look at this graph, these are two of the popular relationships between area, which is on the x-axis, and revenue, which is on the y-axis. And these are the Gompertz and the exponential models. So you see they rapidly increase with area, but then they start leveling off. And in fact, the Gompertz levels off entirely. We chose to use an exponential model. And so an increase in area will always result in increase in revenue, but very much the diminishing return. Okay, so the other thing we have to model is the traffic density. There are very few studies published that actually show traffic density. Why is this? Well, first of all, most stores don't know. They don't track customers as they move through the stores. There are privacy issues. There's also issues of how time consuming that would be. The other thing is if they do have an idea of the traffic density, they don't like to share it because they regard this as a competitive advantage. So on the left here is actually one of the few studies published, and it's not a very good quality graph, but it's a heat graph, and this is of a grocery store. So the blue areas are the least trafficked, the red are the most, the yellow the second most, and the green the third most. So if you look at this, you can see down at the bottom are the checkout lanes, so then everybody has to check out. The entrance is at the bottom right. We look over at the top left, that's as far away from the entrance as you can get. But if you see, there's a lot of customers that go back there, and this is a store from the US, by the way. So what's back there? Well, I can tell, any store in the US is set up like this. It's the dairy. They always put the dairy in the far back corner. I've noticed that's not true in Chile. But the dairy, so things like yogurt, cheese, and milk, always in the back corner because people in the US buy this frequently. And one thing is that you have to know in the US, milk is always bought fresh. It's not like in Chile where you buy it in a box. And so people are continually going for dairy products, especially milk. So they put it in the back. Why? To make customers go through the whole store, so they hope they buy other things. What I found in Chile is things in the back are the bread. So that's another one. So in the US, people buy bread too, but it tends to have more preservatives in it, which is bad for us, but if they last longer. But in Chile, people are buying fresh bread, so they're going to the bread a lot. And then also some of the meats are back there too. So people in Chile like a lot of meat, and they like it, what I could tell, freshly carved, so they're going back there. So it's the same motivation to lay out the store, to bring customers, to force them to go through as much of the real estate as it can. So what we're going to do on the right is to very much simplify that. So this is a crude approximation with our racetrack store. So our racetrack store is going to have one entrance, which you can see at the bottom center. And we're dividing it into three segments. So one segment is the red segment. That we're assuming gets the maximum traffic because everyone has to go in and out of the store. And so naturally, that would be the most traffic. The green are going to be the medium traffic and the blue the least. So you can go and shop in the store and do quite a bit of shopping without ever getting to the blue if you don't want to go back there. So we're dividing it again into three segments in terms of traffic. And we're also going to divide the impulse purchases into three segments too. So we're taking all of the different departments or functional areas in the store and saying, does this have high impulse purchase, medium impulse purchase, or low impulse purchase? So for example, if I think about women's perfumes and fragrances, that's a very high impulse purchase material object. If you go to any department store, I've seen them in Chile, I've seen them in the US and other places worldwide. When you go in, they're right there, right? They're at the high traffic areas. Why? The makeup, and then because women will go, oh, wow, let me try this. And they always have people there, don't you want to see this? And yeah. So, but if you think about, let's say, men's underwear, not such a high profit. They're never at the beginning. They're off in the back. You have to go find it somewhere. Okay. So we're going to try to match impulse purchases to traffic. So this is our revenue model. And the revenue model has the numerator of the big A, which is the area, which is our, this is our exponential model. And then the little r is a revenue multiplier. So for example, some things are more expensive than others. So if I'm going to buy, for example, jewelry, the r is going to be a lot more than if I'm buying underwear, which is a lower cost item. In the denominator, I'm not going to go through all the details, but essentially what we're trying to do is match the impulse purchase category with the traffic category. So if something is a low impulse purchase type, but in a high traffic, it doesn't get penalized. That's okay. But the problem with that is it's taking space away from something that could be higher impulse purchase. But if I have a high impulse purchase type of product, like women's fragrances and makeup, and I'm placing them in the low traffic area, then that's not good. And so that's what this does. This is essentially penalizes for not meeting the impulse purchase with the traffic category. Yes. Yeah.
We have a person here.
Yeah.
Tito Comunero is asking, what about logistics of reloading shelves?
Okay.
One side story said, I once saw a study that suggested that maybe the reason why milk is the back of the store in the U.S. This is to unload from the start.
Okay. So did they hear that, or should I repeat the question? Okay. So Tito is asking about reloading and about the milk being in the back. And I think that's a really good point. Certainly for grocery stores where there's quite a bit of turnover, restocking is an aspect that deserves some consideration. We, in this study with the retailers, with the department stores, we did not consider restocking. And in terms of milk being in the back because of restocking, I don't know, because there's other bulky items that turn over, and I think it's more of a draw to get people through the stores. But I can't say for sure. I will tell you that one of the issues in dealing in this particular application area is it's very hard to get information, because we've contacted retailers and a lot of times they don't really know. They don't do a lot of analytic things. And if they know, they usually don't want to tell you because they're very secretive. So I can't say for sure, but I do appreciate it. And I do note that in this work, we completely ignore with restocking. Yeah. So it's to match it. So so what we're saying is it in the proper zone? Oh, I'm sorry. Yes. Yes, so that would be the high traffic zone. I'm sorry. Yeah, yes. And so we divide it into three. I mean, so we have 3 traffic zones and 3 impulse purchase categories. But you wouldn't have to. I mean, you could have them be different numbers. But we just thought 3 was kind of a balance between capturing that aspect, but without getting too detailed because we didn't really have the data to support all the detail. We also considered adjacency. So we took this directly from the manufacturing literature. This is a so-called REL chart. And adjacency, if we think about it, for example, if I have women's sports clothes, I typically will want them somewhere nearby women's dress clothes. So all of the women's things could be in a similar area. So in that case, I would want them to have a rating of A or E where it was particularly important for them to be adjacent or near each other. But some things I don't want close to each other. So if I have women's underwear, maybe I don't want it next to men's underwear. I mean, it may be a little awkward. And so I might say, let's push those further apart. Some I don't care. And so I will have just a one where I don't care what's next to it. I don't care if toys is next to housewares or next to kids' clothes. I mean, I'm just using an example. So this is taken directly from the manufacturing literature. And what it is a ratio, this epsilon, where the numerator is the adherence to the desired. So we do the user has to do a pairwise comparison, and it's a symmetric matrix. So we do a half matrix, which gives all of the pairwise desired adjacencies for all pairs of departments. And so if it's all of them are adhered to, that's the denominator. And then the numerator are the ones that are actually adhered to in this particular design. And so the epsilon is a maximum of 1, otherwise it's less. And so we take epsilon and we multiply it times the revenue. So essentially, if a store design doesn't fulfill a lot of adjacency, it penalizes the revenue through a multiplier of less than 1. So this is the overall model. A couple things to note here. First of all, we also have this R sub A. That's the revenue of the aisle. So we also included the aisle for revenue, because if you think about, if you walk through a grocery store, department store, sometimes in the aisles are displays, and the aisles can be used for selling items. So we included that possibility. We also have some shape constraints, and I'm going to talk more about that later, but in terms of the relative squareness of departments. We also have a minimum and maximum area. So let's talk about the minimum area, because that's important. So for example, if I was looking at revenue only or profit only, I might say, I don't want to sell any men's underwear. It's not really profitable. Men's socks not making me much money. But to be a full department store, you have to stock some. Otherwise, you're not fulfilling your mission, and customers would be like, what? I can't buy men's socks here? No. So there has to be a minimum space for this. We also have a lower and upper bounds on the width of the aisles, because aisles have to be wide enough to be safe and allow transport, but we have a maximum. The maximum, actually, I don't think we ever encounter, but we use the minimums for these values. That's our model. So then we thought about solving the model. And obviously, for anything bigger than a really teeny department store, you can't solve it exactly. So our goal was to solve it in one big way. And honestly, we couldn't figure out how to do that. I do think there's a way to do it, but we couldn't figure out how to do it. So we broke this into two parts. The first part establishes the sizes of the departments. And we do that, and I think that's on the next slide, through a nonlinear program. The second part then uses the Tabu search to actually do the design of the store, which establishes the shapes, the relative layout, and so on. So I won't be able to talk too much about Tabu search, because I don't have so much time, but probably a lot of you have heard of it and perhaps used it. It's combinatorial. It works best for combinatorial problems, developed by Fred Glover, I guess, wow, probably 30 years ago, more than 20 anyways, and it's quite well established. I like to use it when I have a problem that has what I call a good neighborhood structure. In other words, if I move to a neighboring solution, is the objective function similar? And in this layout, my intuition and judgment was that this was true, that the surface of objective function, if you can think about it in hyperspace, was pretty well behaved. And then Tabu search tends to be pretty efficient and quite controllable in that instance. Could you use other approaches? Absolutely. I'm not here to say Tabu search is the best, but we used it and it works pretty well. So Tabu search, just to give you a brief definition, is basically a greedy search. It's a greedy neighborhood search where you move to the best neighboring solution, with one exception, and that is there's a Tabu list. And so the Tabu list usually stores some aspect of either the move or the new solution, and those are prohibited. So even if it's the best move, if it's on the Tabu, you can't move there. And so it has the property, at least theoretically, of being a global optimizer as opposed to a local optimizer. In practice, for large search spaces, Tabu search works really well, but it tends to actually go to a local optimum. Maybe not the closest, but to a local optimum. And so usually you need some kind of diversification or restart mechanism in the larger spaces to make it more of a global optimizer. And then that's what we did. So these are some of the components: the encoding, the objective function, the move operator, how you evaluate the moves, how are you going to decide when to terminate it. This is another problem. In Tabu search, your final solution is usually not your best solution. And so you have to decide, when should I stop searching? And that's an open issue. And then how long is the Tabu list and what to put on it. And aspiration criteria is, if you're trying to move somewhere that's Tabu, if it's super, super good, should you go ahead and ignore the Tabu and move there? So we use these. This is the little pseudocode, obviously in English here. Tabu search has a nice advantage. It's really easy to code. It's a very simple. Essentially, you start with a random solution, and using your move operator, you consider all the possible moves in the neighborhood. You move to the best one. You record something on the taboo list, and you start again. And so that's the loop. Um, in this case, if the taboo list is actually a moving window, and so once it fills up, the oldest one is removed as new ones are replaced. So it's really a simple code. So this is the nonlinear program. So as I said, we broke this up. And so you could ask me, well, does that mean you're not really truly optimizing because you are breaking things up? And the answer is that's true. Because we just couldn't figure out how to do both parts. So we use Lingo, actually a nonlinear optimizer, to maximize the revenue according to that equation, which we saw earlier, and that establishes the areas. So there's a bounded area, there's a fixed area of the store, that's already known. And then you have minimum areas of all the departments. So then the question is, if you add up all the minimums, they're quite a bit less than the total area. And so how to allocate all the area properly. And so this finds that. And then the A's are fixed. Once the A's are fixed, then it becomes a layout problem. So let me describe the encoding. So if you think about, this is our store here. How do I represent this in a simple string or matrix or whatever? And we represented it with the string that's above it, which you can see is pretty simple. I think it's a pretty compact encoding. Are there other encodings? Yes, but this is what we use. So the encoding simply starts with a sequence. And as you can see, it starts with A, which is towards the lower right, and it wraps around what we call the outer bay of departments A through H, okay? Then we go to the inner bay. We start with I, and we go down along the top, and then we wrap back along from L to N. And so there's a couple things to know here. First of all, the aspect ratio of the inner portion we fix to be the same as the aspect ratio of the store. Okay, so that does reduce the design space, but it's a logical assumption. The other thing is that we only allowed for 2 rows of departments in the inner section. I mean, could you enlarge that? Of course, you would just add the encoding. So the other thing we have to do is the 8 and 11. So if you see the 8 and 11 there, well, if you count departments A through H, you'll discover that's 8 departments. So the 8 means after the 8th department, that's where it ends in the outer bay. The 11 means after the 11th department, so then we have I, J, and K, which are 3 more, that ends the top row bay. So it's pretty simple. It's a combinatorial encoding. It has some interesting effects, though. So let's look at these. So these are some moves. So let's say I wanted to change 2 departments. So that's a very simple move. I want to swap their locations. In this case, we're going to swap L and B, which are already pretty close to each other, right? Well, so we're going to swap L and B. But if I do that, so the original solution is on the left, and on the right is the new solution where I'm swapping L and B. What does this do? Well, L and B are of different areas. And so actually the result is pretty profound because it changes the shape of all of the departments. Because in order to, since L is smaller than B, it makes the outer area, the A through H, actually smaller. So it pushes the aisles out and changes the shape. To accommodate the B where there used to be L, I have to move the divider between the top inner row and the bottom inner row up. So because I have to have more space on the bottom to accommodate B. And so we're getting shape changes even though it's a simple swap. Let's look at one other simple change, and this is simply moving the outer bay, the outer number of departments from 8 to 7. Again, a very simple move. But again, it creates a lot of changes because my area now in the outer is much less. So I'm moving the aisles out, the racetrack aisle, and I've got to now accommodate 4 departments in the upper inner bay, and so that also changes all of that. So it's kind of an interesting encoding. I think it has the advantage of being very, very compact and easy to work with. This effect of a small change in the encoding, the actual realization of an encoding instance, has quite a big effect on the layout, or potentially could. But I don't know if you could avoid that with this type of problem, just because of the way everything is kind of interconnected. So this is the overall. I'm not going to go through this whole little flow chart, but essentially, as I said, we do the areas with lingo, and then we start the taboo search, which is in the green area. We do use a diversification, so we use a kind of a random restart if we kind of don't find anything improving for a long time. The termination criteria is really simple. After so many non-improving moves, then we're done. And our aspiration criteria is the simplest one, that if it's the best solution ever found, we override the taboo list and we accept it. So it's a very straightforward, it's not a fancy or creative taboo search. It's what we call plain vanilla taboo search. So we developed 2 problems. So first of all, I do have to say these aren't real problems, but we were inspired by real problems. We wanted to work with a retailer, or even 2, and contacted some, even with, you know, some fairly good contacts, but we could never get data from them. And there, as I said, there's 2 reasons we found: they didn't have a lot, and they were super protective about it. So we developed a 12 department and a 20 department problem with different areas of the store, different elasticities in terms of the revenue relationships, and so on. In terms of solving, it was pretty straightforward. They ranged from 2 minutes to, you know, well less than an hour. So very manageable computationally. I'm not going to show you a lot of results, but let me show you this one. This is the larger one. And so if you can see on the right, those are our 2 best solutions. So you might say, wait a minute, 2 best solutions. Well, if you look at them, they're a lot different, right? And what's different about them? Which store would you rather shop in, the top one or the bottom one? The top one, yeah. If you look at the bottom one, there's some strange shapes, right? Look at Department J. The Department J, unless I'm displaying like maybe 1 row of books, it would be really difficult to display or to shop in J. The bottom one doesn't have the shape constraints. So without the shape constraints, you tend to get what we call long, skinny departments, which aren't very practical. So the top one has, you can see, quite square, although not totally square shapes, but very reasonable shape. So let's look at the top one. If it's a red color, it means it's a high impulse purchase department. If it's a green color, it's medium impulse. If it's blue, it's a low impulse. So if you see, the red ones are pretty much in the high trafficked area, whereas most of the blue ones are towards the least trafficked. Although we see an exception over there in R. So R is a low impulse item, but it's in high traffic. So you might say, well, that probably didn't optimize too well, but you have to remember we have adjacencies. So that could be something that, say, maybe it's men's underwear, but it's close to, say, men's shirts or men's sportswear, and so they want to keep it together. And to compare our results, and I'm not going to go through all of this, I have a paper you can reference if you're interested. We compared the bounds, and we couldn't get the true optimal because the search space is too big. And, you know, what can we say? We think the optimization itself is really good. Is this the best? I can't say, but it's pretty good, I would say, in terms of optimization. Another thing we did with this is we asked the question, what if you could enlarge the store? So what if you could build a bigger store, or what if you could add on to the store? And so you can also use this to answer that question, which is where I should give the extra area and how I should arrange it. So over on the right is a graph which shows all of these 20 departments, and you can see with an increase in area, and we tried 3 different versions, only some departments got increases. And of course, this was all relative to their likelihood of selling more products with an increase in area. Okay, so the last thing we did with this was to consider 2 objectives. So if you notice, we kind of had 2 objectives, but we forced them together because we had the revenue objective and we had an adjacency objective. So we used the adjacency objective basically as a penalizer for the revenue. But we decided, why not just break them apart and do a by objective? And so we used a method that's me, the Smith over there, with one of my students and a colleague publisher in European Journal of Operations Research, 11 years ago. But it's a general method for Tabu search and for multi-objective problems. And it uses, it's simple. I love simple things if they work. And it simply alternates the objective according to a probability distribution. In this case, we only have 2 objectives. So you simply put a probability on each and you roll a random number each time. In this case, the probability of adhering to P sub A, which is the adjacency, has more of a probability than P sub R. So the probabilities don't have to be equal. We found that if we favored the adjacency, we got better results. Okay, and I'm going to show you some of these. And so what we have here is a Pareto set of solutions. So we looked at the same problems. This is that 20 department problem. In this case, this is the result of one of the optimizations. On the x-axis is the revenue, and on the y-axis is the adjacency. So the ideal point is at the top right. This is where you'd want to maximize adjacency and maximize revenue. But it's always a trade-off. That's what life's about. So you can see here, all of the x's represent optimal solutions. In other words, they're non-dominated. So if we look at these, and there's a couple different designs that we drew depending on the relative revenue versus adjacency. We identified, although this is just not necessarily the right answer, but this one, which is the one that's marked by the adjacency value and the revenue, because you give up hardly anything in adjacency, but it still has a relatively high revenue. But this method gives store designers a small set of very good solutions that they can examine and decide what trade-off is best for them. Okay, so conclusions. There were a lot of simplicities here. I mean, if you look at our racetrack, it's a little bit crude. And also we divided impulse purchases and store traffic into 3 categories each. We use an exponential model, which, is obviously an idealized form that may not be followed in real life. But we captured, we think, the important aspects. We captured the relationship of area to revenue, location to revenue, impulse purchase to revenue, adjacencies. We also were able to maintain reasonable stores. If you look at the store designs, they look reasonable. They look like a store. I mean, you could totally use this design. I mean, you have to do the details, but the block layout is there. So it enforced everything. Computationally, it was very manageable. There weren't big issues with this. The bi-objective version offered, as I said, a small but non-dominated set for further consideration. So one of the issues with this is that we didn't have real data. And so when I finished this work and it was published, I'm going to give you, well, here are the 2 papers. So we published the single objective in IIE transactions and the bi-objective in engineering optimization. They had a special issue on multi-objective meta-heuristics. But I really wanted to further this work, but I also thought one of the big issues was we really need to work with a retailer because we'd like their insights and their data and so on. I was also interested in grocery store layout because we talked a little bit about grocery store, um, but it has some differences from department stores. So I had another student come along and I said, well, I'd like you to work on this, but we really need to try to work with a company if possible. And I'm telling you this story for a purpose. And so she is also from Turkey because I was in Turkey, so I worked with a lot of Turkish students. But now I'm in Chile, and I'm expecting a lot of students from Chile. I'm waiting for more Chilean students to come study with me. So here we can work with Jumbo and Leader and so on. But anyways, I asked the student, I said, do you know anyone at Migros? So Migros is their equivalent of a Jumbo or a Leader. It's Turkey's largest retailer, and it's very big. And I said, like, do you have a relative who works there? Well, she said, no, I don't know anyone who works there. I have no relatives. I was like, oh, okay, well. She says, but I can look on their web page and email them. And I almost said to her, like, really? You've got to be kidding. I mean, come on. But I didn't. You know, I was trying to be a good advisor and not dampen her enthusiasm. I said, okay, yeah, you do that. So she came back like the following week, and she had done just that. She looked on their webpage and emailed the CEO. And the CEO responded to her, like almost immediately, and said, this is a great idea. I'm going to instruct my marketing and planning team to work with you. And so it turns out, we didn't know this, but that CEO was a younger man, especially considering, I mean, he's a really important person, but his background was in industrial engineering. So he had that kind of analytic mindset. It also turned out, again, wholly by coincidence, because he didn't know either, but he got his master's degrees in the US at the same university I got my PhD, because I got to meet him later. So he instructed, you know, his team to work with us, and this was several years ago, and which was great for us because they gave us all the data that we wanted. They would do special tests, and then we were telling them what we're doing, and they would say, yeah, this makes sense, or I'm not sure about this. So we've been working with them for almost 4 years, or about 4 years. And my student actually did finally graduate last year and is a professor back in Turkey, is continuing to work with them. And then we also joined with a smaller group of grocery stores called Eunice, which are also in Turkey, and I have a current student working with that data. We have not yet published a paper on that. We're working on it now, so I can't give you a reference, but it's pretty good. The other thing is I wanted to get back to healthcare. And so I hadn't forgotten about that. But healthcare, I think, is a lot harder. So if you think about facility design, it's really important, but it's not clear what the objectives or even what some of the constraints are. So I have another student who's my student from Mexico who translated these slides. And we decided to work on this together. And again, I didn't want to do it just as academic exercise. So we approached and were able to get a partnership with a company called Health South in the US, which is one of the largest hospital chains. So they have over 100 hospitals in the US. And they have even an architect who specializes that we work with. And so we're able to work with healthcare professionals and architects to get, how do you make decisions on how to lay out or change a hospital? And their hospitals are special. They're not urgent care. They're what's called rehabilitation hospitals. And so people go there for anywhere from a week to maybe a month or two. But they're not doing like operations or emergency care. They do a lot of physical therapy, nursing care, and so on. So we're working with them. Alejandro is my student, and he's been doing a good job, but he's been moving slowly. So we don't have a paper on that yet, but that's in the works. So I'm really excited about continuing this. These are just the front pages of the two papers we did publish on what I just showed you. I will say, in my opinion, the opportunities for analytic work, whether it's data mining, optimization, or some other kind of modeling or solution for this field of facility design and layout for service industries is huge, because there's hardly anything. And if you think about it, any retailer or hospital or some other type of service industry could benefit from, even like a university. Here you have this amazing building and it may be laid out perfectly, but you have to consider adjacencies and how people move and interact through the facility. For me, it's been really nice. You know, I told you my first degree is in civil engineering, so it's kind of brought me back to some of that orientation. But it also involves things like architecture, even psychology and cognitive awareness. So we're working with healthcare. We're actually looking in the literature of how patients respond, say, to outdoor light or something like this. So some of these aspects, although we're considering them not in detail, but they're part of what we're looking at in our work. So I'm going to stop there. I really appreciate the audience, and if there's any more questions, I would be really happy to interact with you. Also, if you want to follow up with me, I'm very sorry I'm not meeting the people in Santiago in person, but I'm easy to find on the web, and I'm very responsive by email. If you want to follow up with email, either you or your students, I would love to talk with you more about the work. And again, hopefully I'll be able to visit in person next year. Thank you.